To understand the process for solving absolute value inequalities by any method, we need to first understand the process for solving them graphically. Here we have a graph of y equals the absolute value of 2x plus 6. We can see that this is the correct graph because it has a y-intercept of 6 and a slope of positive 2 on the positive slope part, and that line is turned into a V right where it touches the x-axis. That's how we get our absolute value V for the graph of an absolute value of a linear function. So y equals the absolute value of 2x plus 6 is the graph that we are given. To solve this first inequality, I need to also graph y equals 4, which is a horizontal line. We'll go ahead and draw this in right here at 4 and label it. Now I need to look at my inequality symbol and interpret that as above or below. This is a less than or equal to, so for above or below, I'm only concerned about the less than part of that. I'm going to think of that as below. That tells me that the solution to this inequality corresponds to the part of the V that is below the line. That would be this segment here and this segment here, which are connected. If I drop those down to the x values that form the endpoints, it looks like it starts at -5 and continues to -1. Therefore, my solution set to this inequality, since we have a less than or equal to, I'm going to consider those closed endpoints, and we want everything that's in between. My solution set to this inequality is going to have square brackets and go from -5 to -1. Remember, the square brackets represent an interval, so this is not just the values -5 and -1, but also everything that is in between. Now, based on this same graph, the same two graphs really, we're going to solve this inequality that's in the other direction. This is a greater than or equal to, and because of the greater than, I'm going to think of this as the word above. For this, I have to identify the portion or portions of the absolute value graph that are above the line. We have one over here, and we have another one over here. Now, the endpoints are the same x values that we had in the previous example, but this time, instead of having one connected interval, it looks like we have two disjoint intervals that point in opposite directions. So to turn this into interval notation, I want to recognize that my first interval starts at -infinity and goes up to -5. My second interval starts at -1 and goes up to positive infinity. I'm going to put those together in a union. So we can see from this graph that two possibilities come up. One is a single interval, and that's if we have the bottom of the V. Another possibility is two disjoint intervals, which is what we get if we have the top of the V. To solve an absolute value inequality symbolically, we do have to classify it as the top of the V or the bottom of the V. So we don't have to draw the graph each time, but we do need to at least think about the graph in order to figure out which of these two cases we have. But before we go on to establishing a process for solving symbolically, let's just consider one special case. We have here the graph of y equals the absolute value of x minus 5. And we have here the graph of y equals -2. We know that in an equation, absolute value of x minus 5 equals -2 has no solution. And that's because these two graphs never intersect. When we're working with an inequality, we have to be a little bit more careful than that. The graphs don't intersect, but that doesn't automatically mean that inequalities involving these two functions don't have any solutions. So let's look at the direction of the inequality in each case. The first one says v, which is the absolute value graph, is below -2. Looking at these two graphs, I can see that the v is never below the line, and because of that, this inequality really does have no solution. The second one, however, the inequality symbol is a greater than, which we would interpret as above. So if I read this as v above line, and I look at the graph and try to highlight the parts of the v that are above the line, well, I can see that this is above the line. I can see that all of this is above the line, and that in fact the whole thing is above the line, right? So if the v is always above the line, then that really means that all real numbers are solutions. The shortest way to answer something for which the solution set is all real numbers is this bold R, which represents the set of real numbers. Can make it look sort of pretty. Or we could indicate that it's the interval from -infinity to infinity. All of these answers have the same meaning. And the reason that it's all real numbers is because the v is always above the line. For every real number x on that x-axis, the v is going to be above the line. So we have to be very cautious with these inequalities and not jump to conclusions just because the equation itself has no solution. So again, assuming that c is a positive number, we've seen what to think about if c is a negative number. We really do have to think about the graph in relation to the line. If c is a positive number, then we have these two cases. If our inequality is of the form absolute value is less than or equal to c, then that means if we kind of picture where the line y equals c would be here, it doesn't really matter where we draw it, just somewhere intersecting the v. Our solution set here is going to be the bottom of the v because of the less than. We want the part of the v that's below the line. If we have the bottom of the v, then we have one interval for our solution set. It might have open brackets, it might have closed brackets. That just depends on whether we have a strict or an inclusive inequality that we started with. In the second case, if our inequality is either greater than or equal to, we would interpret that as the word above. So we would say in both of those cases, we want the part of the v that is above the line, y equals c. Well, the part of the v that's above the line is always going to be in two separate disjoint intervals. And that's why when we have a greater than or equal to, we end up with a solution set that looks like two disjoint intervals. We don't really have to write the plus with our plus infinity, but it's in there just for emphasis, right? We really have one interval starting at -infinity going to the left endpoint, the second interval starting at the right endpoint and going to positive infinity. And in fact, I like this without those plus signs better, so I just took them out. So if we are solving an absolute value inequality symbolically, it's not a strictly symbolic process. There's some symbolic process and there's some classifying and thinking about the graph to figure out what our solution set should look like. The first thing that we need to do is find out what those A and B are that make up our interval endpoints. And the way we do that is that we first solve the related equation. The equation is what I get when I change the inequality symbol to an equals. So the absolute value of 2x plus 1 equals 3. Remember that we solved that equation, since 3 is positive, we solved that equation by setting up two separate equations without the absolute value. In one of them, we keep the 3 exactly as it is. In the other equation, we replace it with a negative 3. And solving these two equations, subtract 1 from both sides all around. I get 2x equals 2 and x equals 1. Here I get 2x equals negative 4. So therefore x is equal to negative 2. If I think about this on a number line, negative 2 is on the left, 1 is on the right. So now I want to think about the v, right? I don't have to draw a perfect graph. I just want to think of this graph as crossing the line at these two x values and figure out what my solution set would look like. Would it be the top of the v or the bottom of the v? Well, the greater than indicates that what I really want is the top of the v, because it's the part that is above the line. Anytime I have the top of the v, I'm going to end up with two disjoint intervals. That's just what the top of a v looks like. And therefore, my solution set looks like the interval from negative infinity up to negative 2. Now I'm going to match the bracket to the inequality. This is an inclusive inequality, so I'll go ahead and use a square bracket here, put in a union symbol, and start over again at 1 and go to positive infinity. So remember that it is not a strictly symbolic process that gets us all the way to the solution set. The process of finding the solutions to the equation is pretty symbolic, but we're not done at that point. We still have some thinking to do in order to solve an inequality. It would be a good idea to pause the video at this point and attempt the next one yourself. I'll go ahead and start working on it now. Solving the equation first, we get negative 4x minus 7 equals 5, and negative 4x minus 7 equals negative 5. Adding 7 to both sides, all around. Gets us negative 4x equals 12, and then dividing by negative 4, we get x equals negative 3. Here we have negative 4x equals 2. Dividing by negative 4 gets me x equals negative 1/2. Again, I'm going to either draw or picture a number line to do this. Negative 3 is to the left of negative 1/2. I need to make sure I get them in the correct order first. And I have a v that I'm picturing here. The direction of the inequality this time is less than. which means I want the bottom of the V. The bottom of the V is this connected part down here. And because of that, I end up with just one interval in my solution set. It is the interval from -3 to -1/2. I'm using open brackets, which are like parentheses here, because we have a strict inequality. But remember, this is not an ordered pair. This is the interval from -3 to -1/2. So it's an infinite set that contains all the numbers in between these two endpoints.